The remainder of this course will focus on probability, but before we get into that, let's just have a quick refresher of sets and how sets work. So this is section 7.2 on sets. The definition we'll go with is just this fairly informal definition of a set is a collection of objects. So a set is a grouping of objects. For example, here behind me I have the set of two elements, -3 and +3. This is a notation we'll usually use. The elements in the set will be sort of inside of these curly brackets, and everything inside tells you these are all of the elements of the set. Here's another set. Monday, Tuesday, Wednesday, Thursday, Friday. Again, sets don't have to be numbers, they're just collections of elements of objects. So here I have the set consisting of what looks like all of the weekdays. And I've got another set listed here. It's the set of elements 2, 4, 6, 8, 10. And then I've got this dotted, these dots here that indicate that we're just going to continue this pattern forever. So these first two sets, this only has 2 elements, this one has 5. These are finite sets. But if I ask you how many elements was in this set, well, you continue this pattern forever, right? So we'd have 12, 14, 16, 18, forever. This is an infinite set. Now there's 2 really common ways to give sets, to describe sets. What I've given you here is usually called the listing method. I'm just listing out every single element in the set. So this is the listing method. I don't really have room to write this, but here we've got the listing method. But there's another way you can describe sets. I really shouldn't have written this here. How about I squeeze it in up here? Listing method. Right. There's another way you can describe sets, and that's just by giving a rule. Giving a rule that describes all of the elements in the set. So for example, this first set, I'm going to write this in a different way. Once again, I'm going to use my curly bracket notation to indicate everything inside is an element of the set. But here's what you usually do. So it'll be the set consisting of all numbers or all elements x, and then this bar is usually read as such that. And now I give you a rule. So it's all elements x such that. How could I describe these? I could describe these as all elements x such that when you square x, you get 9. Right? What numbers are those? What numbers x satisfy this equation? Well, the numbers x satisfying x squared equals 9 would just be plus or minus 3. So this is usually called the rule method for describing sets. So we've got the listing method where you literally just list all of the elements, but then sometimes you just describe your set using a rule. You say it's all elements x such that, which is what this bar means, such that, and then you give a rule that describes all of the elements. So this next one, this looks like the weekdays. I don't want to say every day of the week, it's just the weekdays. So how about we describe this using a rule? We say, okay, this will be all elements x such that x is a weekday. And if you want to write down all the weekdays, you would get exactly the same set back, right? So I'm just describing the set by a rule instead. How about this one? This is x such that x is a positive even integer. How about we go with that? X is a positive even integer. And that rule certainly looks like it describes all of the elements in the set, right? It continues on forever. This is an infinite set. But everything in here, under this pattern, would be all of the positive even integers. So 2 ways to describe sets. Either just list all the elements, or give a rule that describes all of the elements. Alright, so I've been using this terminology already. When I talk about the objects in a set, we usually call the objects in a set the members of the set, or even more commonly, the elements of the set. And mathematicians are notoriously a little bit lazy. Writing that down all the time, saying this as an element of the set, gets a little bit tiresome, so there is symbolic notation for this. Here's the symbol. It's this guy here. So little a, this symbol, and then a would mean a is an element of set A. This is just how you describe this symbolically. So if you want to say an element is actually in the set, you would write it using this symbolic notation. And as usual, just like with not equals, if you want to say it's not an element of the set, you just put a bar through the symbol. Yeah, we'll keep going through more notation, so let's keep going. Alright, so continuing on with our notation, with our terminology, we've got a special set that bears mentioning, that's worth mentioning. It's the set with no elements. So you can have a set that has no objects, no elements in it at all. That's usually called the empty set, right? Quite a nice descriptive notation for it. Or sometimes you'll see people call it the null set, and we're going to denote it with a circle and sort of like a 45-degree slanted line through it. All right. So there's the null set, and you'll sometimes see people use this notation. I don't believe our textbook ever does, but sometimes you'll just see it notated by two curly brackets right next to each other to indicate, using sort of a listing method, that I have a set with nothing in it. All right, so notationally, if two sets have exactly the same elements, doesn't matter which order you list them or anything, it's just do two sets have the same elements in them, yes or no. If they do have exactly the same elements, then we say they're equal as sets. So this is how we describe set equality. And we use the notation A equals B. And if they're not equal, we use the notation A is not equal to B. All right, but more interestingly, I think, with the sets is subsets. So if every element in A, everything in the set A, if that's also in the set B, then we say A is a subset of B. So you can think of B as consisting of all of the elements that are in A, and then possibly plus some more stuff. So if A is a subset of B, we use this notation, A, this symbol right here, looks a bit like a C, but it's somewhat more exaggerated. There's the subset symbol. We use this symbol to indicate that A is a subset of B. You can almost think of it as being contained in it, sort of a everything. Well, we'll get to Venn diagrams in just a moment that really sort of allows you to visualize subsets. But everything in A is also in B. And if it's not a subset, then once again we just put a line through it. A is not a subset of B. Okay, so the first couple of important observations I want to make is know that the empty set is a subset of every set. Right? Why? Well, because nothing is in the empty set, so that would vacuously satisfy this condition that every element in the empty set, which is no elements, is also in every other set. And this is somewhat interesting. If A is a subset of B, so everything in A is also in B, and B is a subset of A, so everything in B is also in A, well, that must mean that they have exactly the same elements. So they're equal as sets, A equals B. And in mathematics, this is often a common method of proving the two sets are equal. You prove that they're both subsets of each other, and therefore they must be equal. So let's do an example. Alright, so here behind me I have three sets, A, B, and C. We'll typically use notation like this to describe or to name sets. We'll typically go with uppercase letters. So A is the set consisting of the elements 0, 2, 4, and 6. B is the set consisting of 0, 1, 2, 3, 4, 5, 6. And C is the set consisting of the elements 2, 6, 0, 4. Alright, so we're just going to make some observations. Let's see. My claim is that A is a subset of B. Why is this? Well, if I'm going to say A is a subset of B, then everything in A should also be in B. So I've got 0 in A, well that's also in B. I've got 2 in A, 2 is also in B. I've got 4 in A, 4 is also in B. I've got 6 in A, 6 is also in B. Right? So 0, 2, 4, 6. So clearly then, A is a subset of B. All right, we're just going to list some properties here. Meanwhile, B is not a subset of A. Not everything in B is in A. For example, the element 1 is in B, but it's not in A. Right? So B is not a subset of A. And this would clearly mean that A and B are not the same set. They're not equal to each other. All right, meanwhile, what about A and C? They're pretty clearly both subsets of each other, right? Everything in A is also in C. and everything in C is also in A, but that would mean they're equal, right? They have exactly the same elements. A has the element 0, 2, 4, 6, and the elements in A, they're listed in a different order, but order doesn't matter, right? It's just about what's in the set. And C also has the elements 0, 2, 4, 6. So A and C are equal as sets. They're literally the same set, just listed in a slightly different order. And we'll just do one more thing that I might observe here. There's quite a few more of these that I could list, but how about the empty set? Note that the empty set is a subset of every set. So for example, the empty set is the subset of set B. It's also a subset of C and so on, right? The empty set is the subset of everything. So visualizing sets is important, and we'll move on to Venn diagrams. So a Venn diagram is a really nice pictorial way of visualizing sets, and usually what you'll have is you'll have some sort of square box that's indicated as U, and U is what's thought of as the universal set. The universal set that contains all of the elements that we might be interested in the situation at hand. So for example, suppose I go with the following. Let's say I want to let U be all the letters of the English alphabet. All right, so letters of the English alphabet. And let's come up with some subsets here. So A. How about we let A be the set consisting of A, B, C, and D. So in a Venn diagram, you usually sort of draw your sets that you're interested in. You draw them in circles. So here's set A. And I've got the elements, let's A, B, C, D. You don't usually draw in your picture the actual elements themselves, but I'm going to do this just to be descriptive in this first example. And let's do another set. Set B, which will consist of the elements D, E, G, H, and how about we go with Y. Okay, so I've got another set here, B, and you'll notice that D is in both of these sets, and D is an element of A and B. So I actually have that A and B sort of overlap somehow. They overlap in the sense that they both contain this element D. So under this picture, D is in both circles, right? D is in the circle consisting of set A and the circle consisting of set B. So this is pictorially represented now by the fact that it lies in both sets. And then I've got all the other elements in B that are not in A. I've got E, G, H, and Y. Okay, and then we've got all of the other letters that are not in A and B, but they're still in the universe. They're still out here in U. What would these be? A, B, C, D, E, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. So out here in the universe, we've got all of these other letters that are not parts of A and B. And this is a typical Venn diagram. Again, you usually wouldn't draw all of your elements or label all of your elements, but this description sort of would tell you what's in each set. Sometimes you'll see in the Venn diagram, this is very common, you'll actually see the number of elements indicated in each set, but we'll get to that. So for now, let's introduce some more notation. We've got set unions. Usually denoted A union B. So A with a cup, B, and this is a brand new set. This is the set, and I'll go with the rule notation here. It's a set of all elements X, such that X is in A or it's in B. So X is in A. Again, using our symbolic notation for X is an element of A, or X is an element of B. This is, in the mathematical sense, we use or to not be exclusive. So or means it's in A, or it's in B, or it could be in both. It's not a problem if it's in both. Alright, so this is the set union. The set union of two sets is, descriptively, it's a set of all elements that are in A or in B. Right? So you just take your sets A and B and you smash them together and you get your set union. So pictorially in a Venn diagram, it would be everything that's in A or it's in B, so it would be everything that I've shaded in yellow here. Right? It's both sets together. We also have another really interesting set operator. It's the set intersection, which is the intersection of both sets. It's A intersect B. So just flip the symbol upside down to get, instead of a cap. And this would be the set of all elements X, such that X is in A and X is in B. So again, it's this nice operator. We take two sets and we build a new set out of it. It's the intersection of both sets, and it's the set consisting of all elements that are in both sets at the same time. So it's got to be in A and in B. So pictorially in a Venn diagram, that would of course be this overlap region here. Alright, it would be everything that's in A and B simultaneously. So in the last example, let's just list these really quickly. The union of A and B, everything in A or in B, would just be take all of these elements together in a single set. Right? So this would be, we've got A, B, C, D. I've already got D listed, so I don't have to list it again, and then E, G, H, and Y. E, G, I'm running out of space here, H, and Y. Meanwhile, the set intersection in the last example, the elements that are in both sets at the same time would just be this element D. Right? So it would be a set consisting of a single element. It would just be the set D. Alright, so Venn diagrams are really nice to have, and this is really how you should be thinking about sets in general. When you think about set unions and set intersections, the intersection is just the overlap region between your two sets, if you think of them in a Venn diagram sense. Alright, so I should have made this observation before I erased everything, but one more observation I want to make is note that if I take the intersection of two sets, so A intersect B, notice that that's a subset of A. Right? The intersection of two sets is the overlap region here, and of course everything in that overlap region is contained in A. By definition of being in the intersection, it's got to be, everything in here has to be in A. Right? So everything in this intersection is a subset of A, but everything in this intersection also has to be in B, so it's a subset of B as well. So notice that we always have this. When you intersect two sets, it's a subset of both. And a little bit more terminology. If the intersection of two sets is empty, if it's the empty set, then we say A and B are disjoint. And pictorially, this would look something like this. In Venn diagrams, I would have two sets A and B that don't overlap at all. Right? Because the intersection has to be empty, there has to be no overlap between them, and this is what disjoint sets look like. They're totally separate from each other. Right? So this is an example of disjoint sets. And we've got one more set operation. We have set unions, set intersections. We also have set complements. So we usually denote like this, A with a little dash after it. So A complement, sometimes read as not A, is all elements X in I'm going to be very precise here, it's all elements X that are in the universe such that X is not an element of A. Hence why A complement would sometimes be read as not A, because it's everything that's not in the set A. Right? For example, let's just, I'll draw this with two sets. So here's A and here's B. Everything in the complement of A would be literally everything in the universe that isn't in A. So it's everything outside of A, so everything in here is outside of A. Notice I'm skipping over the overlap region, the intersection of them, because that's stuff that is in A. But it's also everything in the universe that's not in A, so it's everything way out here too. So it's just everything in this picture except the set A. So there's the complement of a set. It's everything outside of the set. And with that, let's do some examples. All right, so here's an example. Our universal set, the numbers we're sort of looking at and thinking about, the universal set is just the numbers 1 through 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we'll look at these two subsets. We'll look at R as the set consisting of 1, 2, 3, 4, and S is 1, 3, 5, and 7. All right, so for example, if I wanted to look at, say, let's do the intersection of R and S. This is asking what elements are in R and in S simultaneously. Well, 1 is in both of them, so we've got 1. 2 is not in both of them. 2 is in R but not in S. 3 is actually an element of both of them, so 3. 4 is in R but not in S, and then 5 and 7 are in S but not in R, so the intersection is just these two numbers. It's this set consisting of the elements 1 and 3. But I could look at, say, now I could do the union, everything in R or in S. So we'll just take these two sets and mash them together into one bigger set. So everything that's in both of them, we've got 1, 2, 3, 4. I'll just list all the elements in R first. And then in S, we've already taken care of 1 and 3. I already have 1 and 3 listed, but then we've also got 5 and 7. So we just combine R and S into a single set there to make the union. But we don't double count elements. Elements can only be listed once, and the order doesn't really matter. How about we do like S complement? So everything not in S. So what do I have that's in the universe but not in S? Well, I'm missing 2. So not in S would be 2, 4, 6, 8, and 9, I believe. Right? 1 is in S, 3 is in S, 5 is in S, and 7 is in S. So this looks like S complement to me. That's everything in U that isn't in S. And then you can do more stuff, like you could take the intersection of any sets with S complement if you want. We could do, for example, R intersect S complement. So that's everything that's in R and in S complement. And that looks like we've got 2 is in both of them and 4 is in both of them. So this would be the set consisting of 2 and 4. And you could keep playing this game. You could do other complements. How about we just do R union S complement? So everything in R and in S complement. So what do we have? Let's just list R again. We've got 1, 2, 3, 4. And then everything else that's in S complement. We've already taken care of 2 and 4, so we've got 6, 8, and 9. Right, so these are our basic set operations, and you should be able to handle these no problem. You should be able to take intersections of sets, unions of sets, complements, and all combinations thereof. There's one more thing I want to do in this section, which is talk about the numbers of elements in sets, which is really important. So when you're working with an infinite set, it's not that interesting what's the number of elements in the set, it's just it's infinite. But in general with finite sets, you want to know how many elements are in the set. So we'll come up with a notation for this. The number of elements in a set A is denoted by lowercase n of A. Full disclosure, this is the notation our textbook uses. It's actually not the most common notation in the world. The most common notation would be something like this. A with these absolute value bars on either side is the number of elements in A is the more common notation. And the number of elements in a set, the fancy terminology for this is the cardinality of the set. But in any case, we'll go with the book's notation, because this is what you'll be seeing in my math lab for homework and whatnot. So for example, if A is a set consisting of the elements -2, 0, and 2, then the number of elements in the set is obviously 3, right? I've got 3 elements, so n of A is 3. And we'll just do one more example here. So you'll see a lot of these on Venn diagrams. So here's set A, set B, of course here's my universe. And what you'll see in Venn diagrams is not the elements of the set sort of filling in the circles, but you might see some numbers on here that indicate the number of elements in each region. So for example, 18, 4, and 30, and I'll put 13 out here. So these numbers are telling me the numbers in each region, right? So for example, how about A intersect B? How many elements, oops, I need notation for this. How many elements are in A intersect B? Well, I'd look at my Venn diagram, and the 4 here tells me that there's 4 in this overlap region. And this overlap literally represents, it's the intersection of A and B. So I know from this Venn diagram that I have 4 elements in there. How about I do the number of elements in A union B? Well, that would be everything that's in both sets at the same time. Not everything in both sets at the same time, but everything in both sets, period. So we'd have 18 elements here, we've got 4 elements here, and 30 elements here, and those elements make up the union of both of these sets. So we'd have 18 plus 4 plus 30. What's that add up to? 22 plus 30 is 52 elements across both sets. How about I want just the elements in A? Well, I've got 18 elements here, and then I've got 4 more in the intersect region. So in A, just in general, I've got 18 plus 4, which is 22 elements. How about the number of elements in not A intersect B? So A complement intersect B. So what's that? That would be everything not in A, so everything outside of A, everything outside of the circle, but that is in B. So everything not in A, but in B, would be this region here. And so everything in not in A, so in A complement, and in B, would be, there's 30 elements in this region. 30 elements in this region here. It's everything not in A and in B. So this would be 30. How about number of elements not in A and not in B? Alright, so that would be everything outside of A and also everything outside of B. Well, that would give me this region, right? It's got to be outside of A and outside of B, and this number here tells me exactly how many are in this region, 13. So this is what you'll often see on Venn diagrams. You won't see the elements in each set, but you will see numerically notated on here, you'll see numbers that tell you how many elements are in each region. And it's important that you can sort of read off what each region corresponds to, right? For example, it's important that you be able to read off that this region here, corresponding to this number 30, is in fact the complement of A intersect with B. Alright, so we'll do more counting. We'll do more counting of sets and so on, but we'll do a lot of that in the next section. So we'll stop here for now.